Learning Outcome 2, Functions and Algebra, 12.2.7. C. Determine the equations of the tangents to graphs. D. Generate sketch graphs of cubic functions using differentiation to determine the stationary points, maxima, minima, and points of inflection, and the factor theorem and other techniques to determine the intercepts with the x-axis. Welcome to another lesson in our series of calculus. In our earlier lessons, we worked hard to make sense of why calculus was invented and also explored some of the reasons for why it was invented. Today we're going to do something different. We will demonstrate one of the applications of calculus by answering a typical metric question that relies on calculus. Specifically, we're going to sketch a graph of a cubic function and we're going to determine the equation of a tangent to the graph at some point on the graph. MacGyver will be helping us again today. Hi there, MacGyver.
Hi there.
By the end of this lesson, you should be able to sketch the graph of a cubic function and to determine the equation of a tangent to a graph. Let's jump right in by looking at the question we're going to answer today. First, we are asked to sketch the graph of the function and then determine the equation of the tangent to f of x at the point 3, f of 3. Are you ready to work with me on this, MacGyver?
Sure, after all the hard work from the previous lessons, it would be good to apply what we have learned.
I'm glad to hear that. Let's get started. In order to draw the graph of the cubic function, there are three sets of critical values that we need to determine. We want to know the coordinates of the turning points of the graph. If they exist, the intersections with the x-axis and the intersection with the y-axis. I want to start by determining the turning point, because knowing the turning points will help us when it comes to determining the x-intercepts. MacGyver, do you think you can do this for us?
Well, in the previous lessons, we used the derivative of the function when we were looking at the turning points. So I think that is what we should do here.
All right. Why don't you do that then?
All right. First, let me write down the function whose graph we are trying to draw. F of x equals negative x cubed plus 14x squared minus 49x plus 36. Now we need to find the derivative, right?
That's right.
F dashed of x equals, let me leave the negative sign just here. The derivative of x cubed is 3 times x to the power of 3 minus 1. Let me simplify that straight away. It equals negative 3x squared plus 14 times 2, x to the power of 2 minus 1, and again I will simplify that straight away, giving me 28 times x minus 49 times 1 times x to the power of 1 minus 1. Once again, let me simplify that straight away, which gives me 49, and finally, the derivative of a constant is 0. So we are done.
Well done. But now tell me something. Why did you need to determine the derivative?
Well, the derivative gives us the gradient of a tangent of the graph at any point on the graph.
Carry on.
And at the turning points, the tangent is horizontal. It has a gradient of 0. So if I let the derivative equal 0, I'll have an equation to solve, and it's going to give me the x-coordinates of the turning points.
Good thinking. Why don't you try that?
At the turning points.
Hold on a second, MacGyver. Rather than writing turning points, would you mind writing stationary points?
As in standing still?
Precisely. It's a subtle but significant thing. Let me quickly explain. There exist some functions that look like this. They don't actually turn, but the gradient or derivative is still 0 for a moment. So rather than talking about a turning point, we talk about a stationary point. In the case of the function that we are working with, you don't know yet whether the point or points that the derivative will give are actually turning points. So until we know that, we refer to them as stationary points.
Okay, at the stationary points, f dashed of x equals 0, which means that negative 3x squared plus 28x minus 49 should equal 0. Dividing through by negative 1 gives me 3x squared minus 28x plus 49 equals 0. I think we can factorize this. Yes, we can. In the one bracket, we get 3x minus 7. And in the other bracket, we get x minus 7. That means that either 3x minus 7 is equals to 0 or x minus 7 equals to 0. And that gives me that either x equals 7 over 3 or x equals 7.
Good work. Thanks, MacGyver. I'd like to take over from here.
Sure thing.
If I were to draw a very rough sketch of where we are so far, I could draw the x-axis and the y-axis, and I could mark 7 over 3 and 7 on the x-axis. What that tells me is that there is a stationary point, which in this case is a turning point on this vertical dotted line through 7 over 3, and another one on this vertical dotted line through 7. Okay, now that we know that we have turning points and what the x-coordinates of those points are, what do we need to do next?
We need to find the y values of the turning point.
That's right. In other words, we need to know where on this line the turning point is. That is, we're interested in the function values for x equals 7 over 3 and x equals 7. Do you think you can work that out for us, MacGyver?
Yeah, I think so. To find the y values of the turning points, I need to substitute the x value into the function. Let's start with this one. The turning point when x is equals to 7 over 3, f of 7 over 3 equals negative 7 over 3 all cubed plus 14 times 7 over 3 squared minus 49 times 7 over 3 plus 36, which is negative 14,8. So the turning point is 7 over 3 and negative 14,8. Now the other point, when x is equal to 7, then f of 7 equals negative 7 cubed plus 14 times 7 squared minus 49 times 7 plus 36, which is 36. So the turning point is 7 and 36.
Let me add that to the sketch. When x is 7, you have shown that the y value of the turning point is 36, which is about here on the y-axis. So that gives us a turning point here. When x is 7 over 3, you have shown that the y value of the turning point is negative 14,8, which is about here on the y-axis. That gives us a turning point here.
I can't believe you had to do all that work in calculus just to be able to find the x values of the turning point.
Yes, it does seem like a lot of work, but without the calculus, we simply couldn't have done it.
I guess so. So what is next?
Well, I guess that all that is left are the intercepts with the axis, and I'd like to suggest that we do the y-intercept first.
I have a feeling that you've got some plan up your sleeve, but okay. We know that we can find the y-intercept by letting x equal 0. In other words, the y-intercept is at the point 0, f of 0. F of 0 equals negative 0 cubed plus 14 times 0 squared minus 49 times 0 plus 36, which is equal to 36. So the y-intercept is given by the coordinates 0, 36.
Let me add that to the sketch. 0, 36, that is an x value of 0 and a y value of 36. Now I'll show you why I was so keen to work out the turning points and y-intercept first. Look at these points. Although we don't know what the x-intercepts are yet, we know that these points are turning points, and that the graph must pass through the y-intercept, so the graph must look something like this.
That makes sense. I suppose it does give us some idea of what the x-intercepts will be. I mean, there must be one between 0 and 7 over 3. Another between 7 over 3 and 7. And another one that is greater than 7.
And knowing that will help us a lot when we are trying to determine the x-intercept.
Yeah, because when we use the remainder and factor theorem, we need to guess for the first root. Now we can make more educated guesses. For example, there is no point even trying any negative x-intercepts.
That's a really good observation. Why don't you try to find the x-intercepts for us?
Alright, we know that. The x-intercepts are found by solving the equation f of x equals 0, which means that we must solve negative x cubed plus 14x squared minus 49x plus 36 equals 0. Dividing by negative 1 gives x cubed minus 14x squared plus 49x minus 36 equals 0. Now we need to find one factor of the expression on the left. We do that by using the remainder theorem. It's clear from the graph that there is one root between 0 and 7 over 3, which is a little more than 2. So I could try 1 and 2. Let's try 1. Then negative f of 1 equals negative 1 cubed plus 14 times 1 squared minus 49 times 1 plus 36, which is equal to negative 1 plus 14 minus 49 plus 36, which equals 0. Great! So now we know that x minus 1 is a factor, because we get 0 when we substitute 1 for each x, which means that x cubed minus 14 times x squared plus 49x minus 36 equals 0 can be factored as x minus 1 times something. Now I need to factorize by inspection, and I will get x squared minus 13x plus 36, which I can factorize like this, which makes the x-intercepts 1, 0, 4, 0, and 9, 0.
Let me add that to our sketch. So this x-intercept must be 1, this one 4, and this one 9. Now that we have this rough sketch, let me draw a neat sketch that is a little more in scale. There we go, all done.
That's pretty cool. I've never seen a graph like this before. So that's what a cubic function looks like.
That's right. Now we need to deal with the second question. The question of that tangent. If you remember, we were asked to determine the equation of the tangent to f of x at the point 3, f of 3.
So, what we need to do is to think about a point on the graph that has an x value of 3, which is here. And then we need to draw a tangent through it like this. And then our job is to find the equation of this tangent.
So how do you think we should approach this?
To determine the equation of a straight line, we need one of two things. Either we need 2 points on the line, or a point on the line and the gradient of the line. In our case, we can calculate the coordinates of this point, since we already know the function f of x. We either need another point or the gradient of this line.
Let me give you a hint. What have we been doing all of this time?
We have been determining derivatives.
And what is a derivative?
A derivative is the gradient of the tangent to the function at a point on the function. Ah, I see where you're going. We can determine the gradient of this tangent by using the derivative.
Correct. Do you think you could manage to do that for us?
Yeah, I think so. The first thing I need is a point. I know the x-coordinate of the point is 3. So I can calculate the y-coordinate of the point by calculating f of 3. So the point where the tangent meets the graph is 3, negative 12. Now I need the gradient. How do we do that again?
You need to use the derivative to determine the gradient, since the derivative is the gradient of the tangent at a point on the graph.
Oh yeah, that's right. I forgot that for a second. So to do that, I need to calculate f dashed of 3. So the gradient of the tangent is 8. Now all that is left to do is to find the equation of the new line. So the equation of the tangent is y equals 8 times x minus 36.
Excellent, MacGyver. Now I want you to answer one more question for me. I know that we were only asked to determine the equation of the tangent at this point, but from the sketch, it is quite obvious that the line does cut the curve in another place. My question is, can we determine the coordinates of this point of intersection?
Sure, we do that all the time. All we need to do is solve the equations simultaneously. Let me show you. At the point of intersection, I know that the y values of the two graphs will be equal, so it follows that g of x should equal f of x. Oh no, we have another one of those cubic equations. I guess we need to use remainder and factor theorem again.
Before you do that, just hold it there for a second. MacGyver, I want to show you something.
Okay.
Of course, you could use the factor theorem if you like, but before you do that, I would like you to stop and think about the problem for a second.
What do you mean?
Think about that cubic equation that you want to solve. Why are you solving it?
Well, it's because I want to know the points of intersection.
True, but can you be more precise?
Well, I guess that since the equation only has x's in it, the solution of that equation will give me the x values of the point of intersection.
Right. With that in mind, look at the graph again.
But I already know the x value of this point of intersection. And because a straight line is a tangent here, I actually know 2 of the solutions to the equation.
Wonderful. Now apply that to the equation you are solving.
In other words, I already know 2 of the factors, x minus 3 and x minus 3. And I only have to find the last bracket, which is easily done by inspection. And that will have to be... So the other point of intersection is 8, 28. Let me write that on the graph.
Well done. Now let's go over what we have discovered today. In order to draw a sketch graph of a cubic function, we find a number of critical points. It's best to start with any stationary point. This may be turning points or points of inflection, points where the function values are neither increasing nor decreasing, where the gradient of the curve is 0. So first we differentiate the function we want to draw and we put the derivative equal to 0. We then solve the resulting quadratic equation. Where there are two different stationary points, they are turning points, and we can find the y or function values of those turning points by substituting the two roots of the quadratic equation into the original function. Then we find the cut on the y-axis. Plotting the stationary points and the cut on the y-axis gives us some idea of whether there are 1, 2, or 3 cuts on the x-axis. We then factorize the equation, using the factor theorem if necessary. Lastly, we plot the cuts on the x-axis and join the critical points to form the graph of the cubic function. And now it's time for your task. For now, you need to spend some time practicing drawing the graphs of cubic functions. There are 3 that I would like you to try. The third has only one stationary point, which is also the only cut on both axes. Plot a few extra points to see what it looks like. That's all we have time for, so till next time, goodbye.